Yeah, so that's working. I hope you can hear me. If not, please let me know in the chat. So today we're going to do a review regression, Bayesian regression. As you know, if you've taken a class in deep learning or basically any other machine learning class, regression and classification is about 90% of the applications that you will do, and also about 90% of the successful applications in machine learning. And usually you do that with a neural net, and that's totally fine. In this class, I don't want to repeat that exercise. I want to show that supervised learning, regression, and Friday will do classification. That this can always be done also in a Bayesian way. And there are a few advantages to the Bayesian way. For one thing, you see that these cost functions that we use in normal, let's say, non-probabilistic machine learning, cost functions like a sum of squared error, basically follow from model assumptions. Towards the end of the class, I showed that if I take a somewhat different model assumption, I actually turn out to derive another cost function, weighted least square. And you can, of course, go on with this idea. And with every model assumption, basically, you implicitly define your cost function. The Bayesian approach has, of course, some advantages additionally, such as that in principle you can compute the Bayesian evidence, with which would be a measure of how good your model is. Okay, it looks like I'm not seeing my screen anymore. Let me try to do that again. How about this? And that part of the machine learning, the computation of the evidence, I didn't do it in the lecture notes. It is in section 3.4 in Bishop's book, but it doesn't have a very nice closed form answer. So I didn't want to make the lesson very long, but in principle, of course, you can also compute the evidence for your model when you do regression. So having said that, with all these advantages, it's still true that you want to have a much more complex network or a much more complex model than what we did in this lesson, right? There are very large neural network architectures, and it's not so easy to apply the Bayesian method to those networks. Of course, there's a lot of progress in the last few years, and so it's becoming easier and easier now to also do a Bayesian approach to neural networks. But we have not yet updated the lecture notes with the latest state there. So with that, I'm going to turn it to you, and I'm ready for any questions that you may have for this class. And again, you can either open your microphone, maybe go over so the question is, could you maybe go over calculation in 3, application, predictive distribution of the regression lecture notes. So we go to so stage 3, when you do a predictive distribution. So what you do is you say, okay, I have a new data point now, X bullet, and I'm interested in the probability for, let's say, the output Y bullet, given all the data that I've seen. In principle, you don't care about what your weights are, the parameters, right? So we're not going to say, given the weights, I don't care what the weights are, I'm going to integrate them out. Also note that I try to pose, whenever there is a task, I try to pose it as an inference question and then just do inference. So that's what we do here. So this, with the rule of marginalization, can be expanded to this form. So this is really the data generating model, and PW given data is the posterior. I plug that in, and so now in principle, you would say, I have a Gaussian times a Gaussian. So let's just go to the Gaussian multiplication formula. That's not so easy because that assumes that you would have a Y bullet here and a Y bullet here, or a W here and a W here. So we have to do some maneuvering of these Gaussians to make that true. As you see, there is a W here and a W here, so it should be possible. And we do that in basically in two stages. One is we substitute Z equals, well, the inner product of X bullet and W, and we substitute that here. That means this distribution can be written as this distribution, and here WTX can be written as Z. And this left-hand distribution, I can always exchange the argument of the Gaussian with the mean. As you know, the Gaussian function is symmetric with respect to its argument and the mean. So I can exchange that. And now this is a Gaussian in Z times a Gaussian in Z. So now we can go apply the formula, the multiplication formula. What you will get is a Gaussian in Z again, and some constant, or at least some factor, alpha, that is not a function of Z. So I just plugged in here the formula. That's all I did. Now, this is still inside the integration over Z. So this first Gaussian, I can take it out the integral. And this second Gaussian, well, that integrates to 1, a Gaussian probability distribution over Z. If I integrate Z out, that is 1. So the only thing that's left over is this left Gaussian here. And so that's my answer. And yeah, what Mn and sigma n is, well, it's given here, but you get it from basically applying this Gaussian formula. So that's how, I mean, it's quite a calculation. And yeah, so this is not something that I think you can do at an exam from scratch, but I hope you can follow it and you can follow that. Well, the nice thing is there is an analytical answer, right? And you see, for instance, that what you get is the probability distribution for Y given a new input. Has, well, there's of course a mean, but there's also some uncertainty about Y. That uncertainty is due, there's a factor beta minus 1. This was the prior, no, this was process noise. This was the, let's say, my model error, right? Here, when I made my model, here, this is, so here I'm saying, well, the prediction of W times X is going to be a predictor for Y, but it's not going to be precise. So let's allow for some error. Beta minus 1 is the precision. So that's in there. That's always in there. And then, yeah, some extra uncertainty. And this is due to, we have some remaining uncertainty about the parameters W. So there's two sources of uncertainty. That sort of explains this expression. So I'm going to read the chat. Y in the third step, the variance of the second Gaussian contains the X bullet. This, or to go from here to here. Yeah, you just have to sort of, as you can see, Z is a linear combination of X. And if we do a linear combination of, so there is this formula before, what we did is linear transformations of Gaussians. And then this is what happens. You can actually look that up to the variance of, let's say the variance of W. If I multiply with a matrix, in this case, just X transpose, then that matrix, well, the new variant is going to be X transpose SN X bullet. Just look up, go back to the class on the Gaussians, then you'll see that that's how that happens. Okay, there's a lot of other questions. So the next question is, does Bayesian linear prediction predict the next data point or a region in which the next data point is likely to occur? It predicts, yeah, I keep repeating that same phrasing, your state of knowledge about, let's say, Y bullet about a response given X, and assuming that you know X explicitly, right? So there's an assumption here that you know X. X is really just a given data point. There's no uncertainty about that. And then still I have some uncertainty about Y. And that's, as we talked about, there's two reasons. First is the uncertainty in our model, the process. This is the beta. And then, yeah, we have the uncertainty about the parameters. We started with a prior, we ended up with a posterior. We still have some uncertainty there. And that also translates in some additional uncertainty about Y. So yeah, so there is, you could say it predicts a region in which the next data point is likely to occur, but it does so in a really quantifiable way by giving you a probability distribution, right? It's not just a region and it's going to be likely. I actually give for every point on the real line, I give the probability that Y is going to occur there. So the next question. X1, X2 through Xn are data points, but what does the X11, X12, and so on mean in matrix X? So we go up here. The idea is here that I'm not, let's see if I put that. So we say Xn is d-dimensional, right? Usually when you do a regression, you say, okay, your input is a vector. You multiply with here, Xn is a vector here. And you multiply with a vector to get Y, and Y is a scalar. And so now I collect capital N of these data points. So Xn here is the first, let's say the first data point in time, which has, oh, it says here capital M. That means that I should have said here, and I will change that. Xn is an element of Rm. Sorry about that. So I'll make a note. It's the M is the dimension of X. And let's say, so the second subscript is let's say the entry in the vector, and the first script is the time, or basically counts the X of n. And then how is the differential of the variable dw only dz? Why not dz is x dw? So let's okay, yeah. So there you have me. I'm going to have to that I'm going to have to because I mean my first reaction is I agree with you. So I'm going to have to recompute that and then get back to you in probably in Piazza, or I'll update this. I'll write maybe a few lines in between, and then tell you in Piazza it's updated. Is that okay? Because to just say in words now, how you basically have to write it out, and then you'll see it. One thing that I do notice is that I think that even if this is true, and maybe that's what's happening, so that I go from an integral over dw to an integral over z. So even if dz is x times w, the x wouldn't be important, right? It would go out of here. But let me just check that. Is that okay for now? If not, then maybe somebody else can chip in. But I'll go to the next one. The prediction is a probability of y. Why shouldn't we predict a value of y with given x? Yeah, well, if for given, if you knew, you would like to predict a value, and if you have a gun to your head, you would probably take the maximum of this probability distribution or something like that. But technically, the state of knowledge is given by a probability distribution for two reasons. One is that you say up here, you say, I have a model, here's my model, and you say for given x, what I know about y is, well, my prediction for y for my model is w times x, and I add some noise, right? That if I didn't do that, then sure, fine. But then you make the assumption that you have a perfect model. Sorry, I was out of the meeting for a few seconds. So there are two sources of uncertainty here. One is I have put in my model the acknowledgement, or sort of the acknowledgement that that this predictor Wxn is probably not the perfect predictor for what happens in the real world. Right? In the real world, I'm going to collect xn and yn, just making these measurements. And let's just make the assumption that is not 100% linear relationship as I give here. So in order to, but I don't know what that model, what the actual relationship is. So I'm just going to capture that with some uncertainty, with some Gaussian noise. The second is that I may propose this model, but I haven't said what W is. So we use the data to estimate W, and then in a Bayesian context, you still have some uncertainty about what W is. And so there are two sources that if you then apply this model, two sources of uncertainty, and then apply this model, you will have some remaining uncertainty about y. That's just proper reasoning. So there's a remark, rereading or reading Bishop could also help. It was insightful for me. Yeah, absolutely. I totally agree. I personally like Bishop's book. It is, of course, much more verbose and goes into more depth than these notes. These notes are just bullets. My strategy would be to start with the video guide, then do the lecture notes. And if you understand everything, you're done. If not, then indeed go to read the chapter in the Bishop's book. And I hope that's sufficient. Yeah, it certainly helped me a lot. Okay, there's another question. Do we have W after step 2? After step 2, you have W in the sense of you have a posterior for W. The click you have to make in your mind is that we're always talking about your state of knowledge about what good values are for W. If I have a finite amount of observations, a finite data set, then I cannot 100% 100% get the value for W. I will have some remaining uncertainty. I could always get more data later on that would lead to a different value for W. And so how do I deal with that? Well, I deal with that by just keeping a probability distribution for W. It's really a switch that you have to make. I'm not saying that W is a random variable or is a deterministic variable. It's just a variable, and the state of knowledge about proper values is given by a probability distribution. So regarding question 2a for regression, is the noise term neglected here as there is no dependence on beta in the outcome? So let's go to the, I noticed myself as well, there are no answers yet for 4 and 5, and I'll be happy to provide them to add to them. We can also talk a little bit through them, of course. But let's go to 2a. So regarding question 2a, so sorry, 2a, consider a linear. The question is the noise term neglected here, as there is no dependence on beta in the outcome? Consider a linear regression problem with y, x, and w as defined in the notebook. Work out the maximum likelihood solution for linear regression by solving this. Is the noise term neglected here? No, my idea was that I would basically, let's say this is your likelihood function, right? Yeah, this is your likelihood function. So my idea was that you would try to find the maximum of this function. And so there is still beta in here. Now later on in this class, we'll find this maximum likelihood distribution simply by getting rid of alpha. And then this is the maximum likelihood distribution. So my hope is that if you actually try to find the maximum, that you would get, okay. And so what you'll see is indeed it doesn't depend on beta, but that is, yeah, that's just has to do with the fact that the Gaussian is symmetric. And so, and in the maximum likelihood estimation, you so that turns out to coincide with the maximum of the Gaussian. So the beta doesn't matter, but that's just sort of accidental. In principle, it would be the maximum likelihood solution would be a function of all the parameters in the system. In this case, beta is not important, but that's an let's say that is a property of the Gaussian. And then the next question, for exercise 5, no answers were provided. Could we discuss these questions here? Sure, we can. I can also write them in later. I apologize. I had forgotten that the answers weren't here yet. So I'll go through question 5. In the class, we use the following prior for the weights. PW given alpha is a Gaussian over W, zero mean, and with precision alpha. It's also diagonal. So give some considerations for choosing a Gaussian prior for the weights. Well, as was already answered also in Piazza, these considerations are given if you go to the chapter for the Gaussian. If you have to choose, let's say, a distribution, a prior distribution, then among all distributions for a given variance, the Gaussian has the maximum entropy, which kind of means that you take the least amount of make the least amount of further assumptions, or so it is sort of a minimal assumption thing, other than I have some uncertainty, right? And I provide that uncertainty, how much uncertainty with alpha. By setting alpha low to a small value, I say I have a lot of uncertainty. And so that seems like the sort of the least committal assumption. You could have taken another distribution. It will be totally fine. But then if you take another distribution and you have a Gaussian likelihood function, then you might get into trouble getting up with a closed form answer. So why not take the Gaussian? The Gaussian provides opportunities to give you a minimal assumption kind of distribution, and it gives you a closed form answer. And those are some considerations. So that's how I would answer A. We could have chosen a prior with full, not the diagonal covariance matrix. Would that be better? If you had specific knowledge about that, yes, you could. As you see, if we go to the posterior, right, I think this is the posterior variance, right? Yes, yes. So the posterior position, right? So there is an aspect that is basically, this is the prior alpha, and we take a diagonal, and then there is this basically this aspect here, which contains all the data and the lambdas, but this x transpose times x, of course, is the symmetric matrix, but it could be highly non-diagonal. So it doesn't make a whole lot of a difference whether you choose a diagonal or not. I think the main thing is that if you don't have much information about W, you just want to make alpha a small value, and then you basically it means the data is going to take care of what alpha is. But by having it alpha I, you also make sure that it's always invertible. All right, because now I have always something on the diagonal, and so it's not a degenerate matrix, so I make it invertible. I can actually compute a posterior. That's the reason why we choose alpha I on the diagonals. You could add small values to the off diagonals, but I would only do that if you have particular a priori information. Right. By choosing 0 on the off diagonals, you basically say I have 0 information there and let the data decide. Now let's go over C. C, generally we choose alpha to be a small positive number. Give your thoughts on that choice, as opposed to giving a large positive value. I just gave some considerations. By making the alpha small, you let the data decide, or you let the data come in quicker, right? And so if you have no idea what W should be, I think that's a good idea. How about choosing a negative value for alpha? No, I wouldn't do that. We still want, it's still a positive symmetric or positive semi-definite or non-negative matrix, right? This matrix. So you shouldn't choose a negative value. So those are, but I will fill that in later, so you won't forget, or at least you can read about that. Fill in some of these considerations. The choice. Let me say one more thing. The choice for PW alpha is a Gaussian with a small alpha is not mandatory. You can choose something else, right? The best I can do is tell you some considerations, and if you have other considerations, other arguments, and they make sense, you can choose another prior. That's totally fine. These were the considerations I talked to you about that made me choose this prior. It's also let's say the prior that people usually choose from a didactical viewpoint because you get a closed loop answer. Or closed form answer, but it's not necessary that you choose this one. That's not an, you are free to choose. So if we have W, we can directly predict Y. Yeah, but you don't have W, right? That's the idea. The idea is that I start with a model. So here's the idea. You get a data set here, and then I say, I give you a new data point, X bullet, and now make a prediction about Y bullet. Now note that if I give you this data set, that's just a limited amount of information. I didn't tell you, maybe there is another data set y x n plus 1, y n plus 1, all the way until a lot more data. But I just give you this. And I will ask you now, I'll give you a new data point. How do you predict y? So the game you have to play, if you make 0 assumptions, you can say really 0 about y dot or y bullet, right? These data points can be totally unrelated to each other. If you're not willing to make some assumptions, then you cannot say anything about y bullet. So we're going to phrase those assumptions in terms of a model. We're going to say, okay, I'm going to basically making some smoothing assumptions here. What's going to happen between these data points, right? X1 and X2 and X3 are all points on the line. And what happens between X1 and X2, right? It's not in this data set. But by proposing a model like this, I'm basically saying what's happening in between the points that I don't observe, right? This is some kind of a smoothing. So make some assumptions here. And I make these assumptions very explicit. I'm going to say, so this is the relationship between y and x. I don't know exactly what that relationship is. I have some uncertainty, but roughly speaking, y is a linear combination of the inputs and some uncertainty. And the linear combination is basically given by w times xn. And what do I know about w? I don't know everything about w. Before I've seen any of the data, I know this, and we just talked about that. And that completes my set of assumptions. So I have a model, a data generating model, and I have a prior on the parameters. And this data generating model I can write as a likelihood. When I do that, I can import the data, come up with a posterior. And if I'm then honest and do prediction given my data point and given my data set, then this is what I can say about y bullet. And it just turns out that the fact that you didn't have a perfect model, but you assumed some uncertainty, the fact that you don't have perfect knowledge about your parameters, but you have some uncertainty about those parameters, that translates into uncertainty about y dot. So it's not fair to say, if we have w, we can directly predict, because you don't have w, right? That's the game we play. We want to know w, but we can't know w because we have just a finite amount of data. So then I see an answer here, and says, so I know you say, from your answer, it says you just end up with a point estimator like the ML or map estimate, rather than this probability distribution. And from what you write here, I kind of think that you prefer a point estimator for y dot. You want to say y dot is this value. If you are forced to do that, then sure, you can take this probability distribution and you can take the maximum or the mean and you can come up with a point estimate. But if you are honest, then this is just your answer. If you're honest about the amount of knowledge that you know, that you put in your modeling assumptions and the data points, those are your two sources of information that you have. And if you then do honest reasoning, probability theory, just apply some and product rules, then your honest answer is, well, I don't have a point estimate for y dot, for y bullet. I just have a probability distribution. I would like to have a point estimate, but I don't. And if you want to get a point estimate, you can look at that probability distribution and pick the point that you want. But you say, because we generally want to find a value for y. That depends on the application, right? So for instance, you talk here about an earlier chat, you talk about, if we have w, we can directly predict, right? This is what you say. And so my answer is, I don't need to know w. I never pick a value of W. Look at this equation here. I actually integrate out my probability distribution over W. I never had to make a choice for what W is. I come up with a posterior, and then I integrate that posterior away, and I never had to make a choice. And I'm averaging over all possible values for W, and I average, I do it nicely. I weigh each possible values by their probability. This is actually a much more accurate way of doing a prediction for Y. If you cannot accept that, pick any point from the probability distribution that you want. Is argmax PY always a suitable choice? Not always. It depends on your objective. It very often is a good choice, but I can imagine some multimodal distributions, right? That have multiple peaks, and that the max is really way out. And would not be a good representation, or the location of the max would not be a good representation of the distribution. So not always is the maximum a suitable choice. It really depends on what you want to do with with your estimate.
Hi Bert. I was also responding to Oifeng. So the comment on yes, but then you lose the posterior, that was mine in response to Oifeng's.
Okay.
I started the message with Oifeng's name and in Teams, that now it seems like
I see. Yeah.
So sorry. Okay. So I you were getting a lot of messages, so I thought I'd chime in, but
yeah, that's good. That's good. Sorry, I misinterpret that. But I didn't want to put you on the spot, Oifeng, at all. But it's good that you asked this, so it gives me an opportunity to explain it again. And I just didn't see correctly who wrote it. So, are there any other problems in this lesson? What comes after this, the interesting thing, I think these plots are interesting, right? You kind of see here that if you have few data points, your model is much more certain about, let's say, the predictive value for Y than areas where you have no data, right? So that makes total sense. And that's, I think that's what these cylinders kind of, why they look nice. This is also nice, I think, depending on how many data points you've seen. If you would just draw functions, let's say functions W phi x, so just functions, predictive functions, and forget about beta, and forget about the certainty about W. I just draw a W and I plot W times phi x. Then I get these wild functions. But when I have a lot of data, all these wild functions kind of look alike. And the more data I get, the more certain I am about what basically the relationship is between X and Y. And then, the other thing in this class is just that I want to show that these ideas of how to choose a cost function, that you don't have to do that. You have to choose a model. The cost function is sort of emerges from that, right? In this case, for instance, the sum of squared errors emerges from using a Gaussian distribution for your uncertainty, and also that they combine in an independent, identical way. Yeah, so I've been talking already a lot, maybe too much, but if there's any other questions, please just go ahead. Exercise 2A. So let's go to exercise 2A. What is log py xw before you take the gradient, and where it can be found? I will update this a little bit because it probably, as defined in the notebook, is a little too lazy from me. I meant just this model, right? This model. But I'll specify the model. I will update 2A and I will add some answers to 4 and 5. Yeah, this is the lazy way of answering the questions. That's pretty clear. So we'll fix that. And then with that, what you will need is this appendix C, I think, in Bishop for the, I mean, if everything would be scalar, you could just do your derivative yourself, no problem. But with matrices, yeah, there's always these problems with traces and whatever. So, and what is the sequence and a transpose sign? So it's better than to just look at the rules in appendix C, or I think they're also given in the previous lecture at the end somewhat. Okay, so last chances to pose a question. All right, so the other thing I needed to remind you is that I think you have until tomorrow to make a choice whether you want to take the exam at home, and that at home means it's an online exam with proctoring software. Basically, it takes over your browser, or on campus. Now, on campus is an option that may go away, right? So it may be that the university may just say a day before, sorry, it's just not allowed, or we can't do it. You can always switch from on campus to online, but you can't switch the other way around. So if you choose, I'm going to take it at home, then you can't a day before the exam say, oh, I'm going to take it on campus, right? So be careful about that. If you really want to be sure, you want to take it on campus, well, we can't be sure, but if you actually want to go for that option, then you should respond to the poll or the question in Canvas, and note your preference. The exam is going to be the same, so that there's no difference in that. And I haven't made the exam, but I plan to make it multiple choice. So it's just going to be setting crosses, and on the side you can make all your calculations. I don't think I'm going to ask you to upload all your calculations. That's just too much work. Because there have been problems with people uploading files. So I'm just going to ask you to do your calculations and click the right answer. And you can do that online or on campus. It makes no difference to me. Yeah, with that, if there's no other question, then I'm going to basically end this session. Friday, we'll do classification. There's the scheduling is that it's basically 2 classes, right? Both generative classification and another way, discriminative classification. So yes, I'll get to that question. So I'll warn you that It's a little bit more than, let's say, the regression. It just turned out that in order to fit everything what I wanted to do in the program, I had to put some classes together, and the two ways of doing classification seem to be a nice way to combine it. So I'm sorry, it's a bit more than usual. There's a weekend afterwards. And it's not really a lot, but still it might be a bit more than usual. So then there's a question, has there already been a decision on if the programming assignments will count towards the grade? Yes, so in the beginning of the class, I said what we'll do is, so we do multiple choice, and you just get the grade what you get, right? Done. Unless the grade is between 5.0 and 5.4, then I said, okay, then I will look at your Piazza involvement, and based on my impression there, I may upgrade you to 5.5 and you get a 6. And that's, so then you pass. And so we decided to do a similar thing with the programming assignments. So normally they don't count. If you want to skip the programming assignments, you can get a 10. If you pass, if you do all the, let's say all the multiple choice questions correct, you get a 10. However, if you're going to be between 4.5 and 5.4, then I'm going to look at your programming assignments and Piazza, and you may actually get up if everything goes perfect. We're really involved. I may even decide to upgrade you from 4.5 to 5.5. So the maximum you will get is 1 point. But we'll look at both your programming, how you did on the programming assignments, and on your Piazza involvement. And they both count, let's say, maximally for a half a point, right? Maximally, if you. So it's an. Yeah, it's basically a credit that you only can get if you are. Yeah, if you just seem to be failing the class. That's the decision we made, just to get a few more people over the point of passing. But you're going to have to show that you really worked for the class during the let's say during the class. Does that answer that? And to be sure, I will also announce that then in Piazza, so then we can be certain about that. Okay. Yeah. I think you should do the programming assignments, not just for the potential upgrade, also because we may actually ask programming assignment or code in our questions on the exam. You may get a piece of code, and there could be, let's say, under A could be, and the question could be, okay, which piece of code should be inserted in this place? And I could give you A, B, C, or D, 4 pieces that you could insert, and then you have to make a choice. So there, it helps to do the programming assignments. It also helps probably to understand the material. So if you have time, then you're really encouraged to do that as well. Okay. If I don't see anything in 5 seconds, or see somebody typing, then I'm going to finish the class today, and wish you a great evening, and good luck in studying the material for the classification class, and then we'll see you on Friday. Bye-bye.